Here we're going to take a look at a graph of the derivative and the second derivative and see if we can find relative extrema and inflection points. So this information should be able to give us the locations of some relative extrema and inflection points. Essentially, let's take a look at this graph. All right, so this one here is our first derivative, and this one here is our second derivative. So again, there's a lot of information in here, and so what I'm going to do is I'm going to actually just create what we would have done if we analyze this function analytically. I'm going to say, okay, let's look at a first derivative number line. Where is the first derivative 0 or undefined? Well, the first derivative is 0 there and there. So -1 and 1 would be critical numbers to go on our chart here. And then we'd be asking, what are the signs of the derivative in these different regions? Well, if we look in this leftmost region here, the function, the derivative function, is always above the axis, so it's always positive there. It's negative in the region between -1 and 1, and it's positive in the region after 1. So I got everything that I was looking for there, and essentially I know that it was increasing before -1 and then decreasing afterwards, making -1 a relative maximum. And it was decreasing before 1 and then increasing after, making 1 a relative minimum. So I'm able to find that these are relative extrema of the original function f. I could do a similar thing now with the second derivative. All right, let's look back at the graph here. So the second derivative, where is it 0 or undefined? Well, it's 0 at 0. Okay, well, sorry, I was usually putting lines in there. Okay, and what are its signs? Well, the second derivative, now we're just looking at this line here, this second derivative is negative below 0 and positive above 0. So it's negative below 0 and positive above 0, meaning that f is concave down here and f is concave up here. And in fact, we do have a change in concavity here at 0. So we do have an inflection point at x equals 0. All right, so interestingly enough, we can't get any y values here, but we can conclude that we had a relative max where x is -1, we had a relative min where x is 1, and we had an inflection point where x is 0. All right, so we were able to do that without the original function because we were able to analyze these derivative charts based on the location of zeros and the positive or negative nature of each one of these functions. Okay, so there you go. All right, so let's move on to this one. So an optimization problem here. Rectangular package to be sent by a postal service can have a maximum combined length and girth. So the girth is the perimeter of the cross-section. So on the diagram, that would be this perimeter here of 108 inches. Find the dimensions of the package of maximum volume that can be sent, assuming the cross-section is square. Okay, so what do we want to do? We want to maximize volume. All right, and let's take a look. So we already have some dimensions here. So because we said that the cross-section is going to be square, we have that as x by x. and then we have the length of this package as y. Okay, so that means that we could write the volume as, so it would be the x times the x, giving us x squared for the area of that cross section, times the y to give x squared y as the volume. All right, so that's for the volume there. And do we have any restrictions? Well, yeah, I can have a maximum combined length and girth of 108. So this length is y. So what we have is y plus the perimeter of the cross section. Well, that's the perimeter, again, of this. So that's x plus x plus x plus x. So that's 4x is 108. All right. So that means that we can now get y is 108 minus 4x, which will allow us to bring now our volume equation to be v equals x squared times 108 minus 4x, and we've been able to eliminate the x and get a function of one variable. So we have v of x is 108 x squared minus 4x cubed. And notice that what are the restrictions? Well, certainly x has to be bigger than 0. In theory, it can go off to infinity, but because, and that's because y could get really, really tiny. It's unlikely that this is going to happen, but we have to at least entertain the idea that x could go off to infinity. Okay, so our problem really becomes maximize v of x equals 108 x squared minus 4x cubed on 0 infinity. So we need the derivative, which would be 216x minus 12x squared, which would be, factor out a 12x, and that's 8 minus x. So we do our normal thing and ask when is the derivative equal to 0. X equals 0 and x equals 8. Now x equals 0 we're not actually going to use because it's not on our domain here, but we'll use, oh, I'm sorry, that's not 8, that's 18. 12 times 18 is 216. So x is 18 is our other critical number here. And is there any place where the derivative is undefined where the original function was defined? No. So let's take a look at putting this, all right, from 0 to infinity. So this is now v prime. We'll put 8 on there. I keep saying 8, 18, sorry. So if we take 1, say, and put it into our derivative, we'll get a positive times a positive. If we take something bigger than 18, this is still going to be positive, but now this is going to go negative, so it's negative there. And so we would have increasing before, decreasing after. So that would make this a relative max. But because it's always increasing before and decreasing after, this would have to also be our absolute max, telling me that I should take x to be 18. Now, if x is 18, y is 108 minus 4x. And that's going to give a y of 36. And so there we have it. We have our dimensions. Remember, it was x by x, so 18 by 18 by 36. And that will give us the package of maximum volume under these restrictions. That's it.